15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, once again, welcome. Thank you for joining us on the Space Nuts podcast, episode 226. My name is Andrew Dunkley, and joining me as always is the good Professor Fred Watson, astronomer at large. Hello, Fred.
I'm delighted to be thought of as good.
It's always good to be good.
Yeah, sometimes people think I'm rubbish. So there you go. Thank you, Andrew.
I don't believe that for one moment, and I know that at least 3 people who listen to our podcast feel the same. Now, today we're going to be talking about a couple of stories that are big in astronomical news this week. One that they've been teasing us about and finally announced, and that is that there might be more water on the moon than we first thought. And while we're on the moon, we're going to talk about that collaboration between NASA and Nokia to put a 4G network, a mobile phone network on the moon. They're deadly serious about it, but radio astronomers are not too thrilled. And we're going to revisit, as promised, the OSIRIS-REx mission, which successfully bounced off asteroid Bennu, kicked up the dust, collected some samples, and looks like they might have got too much because they can't get the lid on. So we'll see what's happening there. And a couple of really interesting questions, one about the use of the sun as a gravitational lens, and another as to why, after the summer solstice in the Southern Hemisphere, the sun still continues to set later, which is a little bit of a confusing anomaly. We'll explain all of that and much, much more today on Space Nuts. Now, Fred, you were on a bit of a road trip last week, were you not?
Indeed, yes, I was. Down in the south of the state, we visited the sites of Canberra, the astronomical sites of Canberra, which included Mount Stromlo Observatory. Had a look at some of the sad remains of telescopes after the fire that went through there in 2003, but also spoke to our group about what's going on there now, which is great stuff. Then we went to Tidbinbilla, to the tracking station, which is part of the NASA Deep Space Network, along with Goldstone and Madrid. Tidbinbilla provides the coverage for deep space vehicles at our longitude. And they've got some very impressive dishes there, including 3 new ones, which work in a slightly different way from the old ones. But one thing that was a highlight of our visit, and I might give a shout out to Glenn Nagel, who's a good friend and somebody who he's actually head of communications at Tidbinbilla, and that's communications and outreach. He gave up his Sunday for us a week ago last Sunday to give us the full tour, which was brilliant. The highlight of the tour for so many people was the old Honeysuckle Creek dish, which was moved to Tidbinbilla. It doesn't operate anymore, but that was the one that got the first signals from Apollo 11 when the astronauts walked on the moon. Despite what the movie says, it was Honeysuckle Creek first, and then the dish.
Yes, that's right. Yeah. I think people in the know that, but they certainly portrayed it as the Parkes Radio Telescope, and it was instrumental in getting signals out as well. So. Yes. Australia played a very big part in the Apollo 11 landings, and fantastic. Don't you love, Fred, the Australian names, Tidbinbilla, and some of the Aboriginal names that get attached to things. Where I live in Dubbo, well, the word Dubbo is supposed to be, and I think they've always had trouble really confirming this, but it's supposed to mean red earth in the Windjawara Windji, in the local Aboriginal language. Red earth because this region is red soil until you get further out west when it turns black and gets very sticky when it rains. Yep. We have some really amazing street names in Dubbo too, Fred. We've got Windjawara Street, which I believe, I'm just trying to remember the meaning of it. We've got another one called Wylandra. Now, I think that means swamp. And we've got another one called Bulch Street. They're all Aboriginal words from the local culture, the Wiradjuri language. So, they've been used here. And a lot of our street signs are made up with local Aboriginal art as well. So, capturing the local culture, I think it's terrific.
Yeah. So when I lived in Coonabarabran, of course, that too is it's a Gomeroi word. Do you know what it means, Coonabarabran?
I do not, but I'm going to think it's something to do with mountains.
It's even more appropriate than that. It's inquisitive person.
Oh, okay. Oh, that's perfect.
Yeah,
that is perfect for astronomy, isn't it?
To be there, isn't it? It's great. Yeah.
Love it.
So just continuing the story, we then spent some time in the snowy mountains, and there was still a little bit of snow, and then down to the coast where we saw things that I've never seen before, some extraordinary places down in Eden and finally up to Bateman's Bay, parts of Wales that I've never explored before. And the best thing was, despite the fact that the Bureau of Meteorology forecast doom and gloom weather conditions for the whole week, it was perfectly fine the whole time. It was great.
Yeah, well, they got them up north instead, and I'm very sad to say that we were talking about the cropping around here recently and how there's just crops as far as the eye can see, and they just needed a couple of weeks of dry weather to get the crops in.
That's right.
Sadly, a couple of areas have been absolutely decimated by hailstorms, so that's very, very sad news indeed. Hopefully they can get those crops off because they desperately need a good season. We haven't had one for 3 or 4 years. Let's get on to our first topic, Fred. I mean, I could talk about Australian history and information for ages. The hidden pockets of water that may exist on the moon. This is a story that's finally, they were teasing us for a good week or so leading up to this, but NASA has made the announcement that there might be a lot more water there than they first thought.
That's right. And there are actually 2 discoveries involved with this, of which one is confirmation, that the infrared signal that we see when you use infrared telescopes to look at the moon, that infrared signal comes actually from water, because earlier results dating from about 2009 were ambiguous. It could have been either H2O, water, or the OH radical, the hydroxyl radical, which in some ways is a form of water. It's a combination of hydrogen and oxygen, but it's not water as we know it. So the signal that was detected back in 2009 could have been either. People assumed it was water, but now it has been confirmed. And it's been confirmed actually by a fascinating telescope that one of my colleagues has used several times. It's a NASA facility. It is a telescope built into the after section of a 747 SP, the old special performance 747s. This is probably quite an elderly aircraft, but it's been modified to have a large telescope poking through a huge hole in the back. It's probably...
Oh, yes, I know the one. Yeah.
Several meters in diameter, in square. In fact, it's a 2.4 meter telescope. It's a 100-inch telescope that they've got mounted in the back of this 747. The aircraft is called SOFIA, which is the Stratospheric Observatory for Infrared Astronomy. Lovely acronym. And it flies from time to time to make observations, usually at heights in the region of 45,000 feet. You're up there in the above all the moisture, virtually all the moisture in the Earth's atmosphere, which is where you can make these fine mid-infrared observations. And so it was SOFIA observations that were used by astronomers, I think based in the University of Hawaii, to detect this infrared signal that is categorically from H2O rather than OH. So we know that it is water that's there. Now, the extraordinary thing is that that work has been done sort of in conjunction, or certainly parallel, with work that has been carried out by scientists, I think at the University of Colorado, I beg your pardon, if I remember rightly.
Colorado's the next state across.
Yeah, that's right. It's Paul Hain of the University of Colorado who's led this paper, which is so what they've done is looked at the areas of the moon that are in permanent shadow, because that's where we think this water is mostly concentrated as ice. Although it's possible there might be liquid water, of course, not open to the to the emptiness of space, probably trapped inside minerals, maybe even mineral glasses. It sounds bizarre, but that sort of thing can happen when meteorites impact the surface of the moon. So you might have liquid water trapped in tiny vials of volcanic or meteoroidal glass. Anyway, probably the bulk of it will be in the form of ice, either bound up with the soil, the soil grains, or maybe even certainly in the base of some of the bigger craters that never see sunlight, maybe even as sheets of ice, because Lunar Reconnaissance Orbiter, the NASA spacecraft that orbits the moon, still active, has detected radar signals or radar returns from those very deep polar craters that suggest that what you're looking at is a surface that's basically shiny, very, very smooth and shiny, so maybe sheets of ice. And the reason why that ice is stable is because, as I said, these crater floors never see the light of day. They never see the sun. The temperature, because of that, can get as low as minus 250 degrees Celsius. You might want to convert that into Fahrenheit, but I'm not going to do it in my head. Minus 250 degrees Celsius, that's 30 degrees or so, 20 or 30 degrees above absolute zero. It's very, very cold. And so the ice is essentially stable. It's just like a rocky surface. So that's where perhaps the bulk of this water is. But this other paper, this Paul Hain paper et al. From the University of Colorado, what they've done, as I was about to say, they've looked at what they called cold traps, a place that is in permanent shadow. And it doesn't have to be in the floor of a crater. They're all in the polar regions of the moon. But they don't have to be in craters, because you can imagine a situation where you've got a hill or even something smaller like a boulder that casts a permanent shadow where you are never going to see sunlight. And so what they've done is they've looked at the surface of the moon, of course, which is very well mapped by things like the Lunar Reconnaissance Orbiter, and they've worked out where these places of permanent shadow are, down to a scale of 1 centimeter.
Wow.
They come to the conclusion that 40,000 square kilometers of the moon's surface is in permanent shadow and contains these cold traps, which range from the floors of craters to something a centimetre across. They reckon there are billions of them, basically. And what that means, when you combine that with the idea that you've got probably in most of these permanent shadow regions, you've probably got the ice because the signal is so strong, then you can calculate how much water there is on the moon. And they're talking somewhere in the region of 2 to 3 billion tons of water.
Good grief.
Which is a big resource. And of course, that is exciting for would-be explorers of the moon, because not only is water something that will support habitation, it also is rocket fuel, because you use sunlight to generate electricity to electrolyze it so that you've got the component hydrogen and oxygen atoms, then you recombine them, that gives you rocket fuel. So there is work already being done on making a business case for the exploration of the moon in terms of using it as a fuel depot. It's extraordinary.
Yes, indeed. And FYI, 418 degrees below zero in Fahrenheit.
Thank you for that.
That's the number you were looking for.
I hoped you'd be.
Which is damn cold.
Damn cold, that's right.
Damn cold, yeah. Actually, the discovery of water on the moon was portrayed in that TV series I was telling you about a couple of weeks ago, For All Mankind, the alternative history series where Russia landed first. They also landed the first female on the moon. The Americans set up a base near a crater to try and sort of take the lead in the space race, and they discovered water in a lava tube in a crater, and water ice. And they, so the whole story of establishing a base was built around the discovery of ice. And we're talking back in the 70s when they supposedly set up a human base on the moon, which in the alternative reality of the movie is feasible, but I think would have been in the realms of science fiction in reality. Probably not today, but back then for sure.
Yeah.
But fascinating series if anyone wants to watch it. It's really well done, highly professional, great acting, and just a really fascinating storyline. And some of the political storylines within it are fascinating too, as to who's the president at various times. And, I think you'll find it most surprising. I think it's on Apple TV, if I recall. But really enjoyable show, really, really just mesmerising. I just loved it. And hopefully they'll make a second season. Are we done with that topic, Fred? No, actually, we're not, because aside from water on the moon, they are now looking at putting a 4G mobile phone network or cell network on the moon with the support of Nokia, which has got a few people upset in the astronomical world.
Yeah, so it sort of almost follows on from what we were just saying. It's the Artemis project, NASA's Artemis project, which is aiming to send the first woman and the next man to the moon in 2024. That project is aiming actually at this southern polar region of the moon, so they hopefully will find out for certain what form this ice is in. But part of the project is to build a sort of, a kind of permanent base on the moon, a permanently inhabited base, with a view to learning about long-term space flight, principally with the idea of going to Mars in the next decade. So the Artemis program is actually, a pretty broad brush thing, and envisages lunar landers and maybe habitation modules actually sitting permanently on the moon's surface. So what has happened is that NASA has recognized that if you've got astronauts wandering around on lunar rovers and things of that sort, trying to find their way without the benefit of GPS, the need is for solid communications. And what NASA has done, is to basically contract Nokia, the Nokia company, actually the American Nokia company, to develop a cellular network on the moon. And it's to facilitate, as I said, long-term lunar habitability, providing communications for key aspects such as lunar rovers and navigation. The lunar 4G network. So that contract's already been awarded, $14.1 million to develop that network. And the immediate consequence was a lot of very upset radio astronomers, because radio astronomy uses the most sensitive antennas in the world to look at signals from deep space, which would be basically flooded out by the Nokia cell net at specific frequencies. This is one thing that we have to be clear about. It's not like flooding something on the ground with white light where you've got every frequency represented. These communications frequencies are quite specific, but at least one of them, and it's certainly one that the Starlink network is using, is very close to a radio astronomy band of interest. And it's of interest because it's where a lot of organic molecules actually emit their radio waves deep in space, precursors for life, things of that sort, which, of course, radio astronomers are really interested in. And if we're going to be flooded out in those wave bands by communications either from constellations of spacecraft above the Earth or by phone networks on the moon, we are struggling. We're going to be struggling. And I think radio astronomers are going to have to be working with the communications people to try and mitigate the consequences of all this. It's already happening, in fact, certainly with SpaceX. I'm sure radio astronomers are talking to Nokia as well about what the lunar, the lunar proposal might look like.
Yeah, I hope they can come to some sort of agreement or understanding. It would be a terrible thing to have basically an arm cut off by radio signals from satellites and a lunar 4G network, and lose that connectivity with the potential of discovery. I think that would be a really big, giant leap backwards. The big question from me, though, Fred, is with this 4G network on the moon, will the astronauts be able to phone home?
Probably.
I had to ask. Someone had to ask.
Somebody has to ask whether they can phone home, except they're not.
Yes.
They're 80s.
Yes, exactly. All right. You're listening to the Space Nuts podcast. Andrew Dunkley here with Fred Watson.
3, 2, 1.
Space Nuts.
Now, before we get on to our next topic, I've got some exciting news, Fred. I'm a little bit thrilled. As you know, I released earlier this year another science fiction novel called The Terrain Enigma, and I decided after much pressure, or several requests, let's call it that, to put it into audio form, which took me a long time, but it finally got released and is out there on Google Books and Apple Audio. I am very pleased to be able to say that it's now on Audible. A lot of people use Audible, which is an Amazon company, to download their books, and a few people have been waiting for me to be able to say that it's on Audible, and yes, it is. So it's on audible.com. It's also available in Australia on audible.com.au. So if you'd like to download the audio edition of the Terrain Enigma, it is now available on just about every audio book platform, but now on audible.com and audible.com.au. I'm very excited about that.
It's great, Andrew, and congratulations for that.
Thank you.
Getting on Audible is a big coup. That's fantastic.
Yeah, and it's damn hard work. I mean, I know I've been in radio for a long time, and doing voice work goes with the gig, but recording an audio book is a completely different animal, and it really can be quite taxing. And I think I've mentioned before that it takes, when you're doing it by yourself and you haven't got the backing of a studio or a producer or an editor or all that, you've really got to do everything yourself, which I did in this spot where I'm sitting on this microphone that I'm talking to you on. So you've got to bring quality into play and try and keep it all at the same standard, even though you're recording segments weeks and weeks and weeks apart. But then you've got to watch out for getting a cold and your voice changing or losing your voice, or there are all sorts of and hay fever, because it can all change. There's a lot of pitfalls, but the big struggle I had, and I didn't bother to fix it, was as I sort of got into the story and was recording a segment weeks after recording another segment, I couldn't remember what voice I used for the character. So I thought, no, blow it. I'll just go with something else and hope that it's the same. But yeah, I just left it. And actually, I had a bit of feedback from someone who listened to it, and they loved it. And I said, yeah, I was a bit worried about the character voices, and they went, oh, we didn't notice. So that's good. Probably shouldn't have mentioned it. But anyway, it's great fun. But being someone who hates editing, that's the hard slog. The editing takes longer than actually reading a chapter and recording it. Yeah, unless you're really good at reading and don't make mistakes, but that's very unlikely for most people, even the best in the business. Now, Fred, let's get on to the OSIRIS-REx mission. This was a mission where we sent the OSIRIS-REx probe to the asteroid Bennu, which it sort of hung around looking at for a good long while, up until last week when they decided, okay, we're going to land on this thing and take a sample. Well, it was a success until it maybe wasn't. Houston, we have a problem.
Yeah.
Hopefully not a long-term problem. Hopefully solvable. But I think the bottom line is they were too successful. Would that be a way of describing it?
So just to recap, the device that they use, so the spacecraft itself approaches the surface of asteroid Bennu, or did this last week, in fact, with a kind of almost like a miniature backhoe arm stretched out, which contains a device on the end, which is called TAGSAM. And TAGSAM is an acronym for Touch and Go Sample Acquisition Mechanism. It's great. I love it.
I don't mind that one.
No,
I don't mind that one at all.
Yeah, it's got that sort of feeling of, just touching the surface to it, hasn't it? TAGSAM.
Yeah, tag, like the game.
Like the game, exactly. So, so this is sort of shaped like a pan, which collects the sample, and then there apparently is a mylar flap, which is meant to seal shut once the sample has been collected. But they were so successful with the TAGSAM that some of the bigger bits of soil and dirt that didn't go through the flap properly have wedged it open.
No.
They've collected more than they expected to. And that essentially means that, first of all, they had the possibility of collecting, if they didn't feel they'd got enough, they had the possibility of collecting another sample in January, I think the 11th of January. But that, I think, has now been ditched because they feel they've got enough. In fact, as the NASA bulletin says, because the first sample collection event was so successful, NASA's Science Mission Directorate has given the mission team the go-ahead to expedite sample stowage. Originally scheduled for the 2nd of November, in the spacecraft's sample return capsule to minimize further sample loss. So there's this separate capsule, the SRC, the sample return capsule, which they've got to stow the sample in. And there's a quote from Dante Loretta, who's the principal investigator for OSIRIS-REx, University of Arizona. The abundance of material we collected from Bennu made it possible to expedite our decision to stow. This team is now working around the clock to accelerate the stowage timeline so we can protect as much of this material as possible for return to Earth. Now, this is where it gets tricky, because what was expected to happen with this stowage procedure was that OSIRIS-REx would run autonomously through a sequence of events. And so what they're doing now is saying, no, we don't want that to happen. We want this to be done so carefully enough that we don't lose soil to space. So they're going to do it all by hand. In other words, send a command, watch what happens, and then send the next command, watch what happens. The problem is you've got a 37-minute delay between sending the command and knowing what it's done, because the signal travel time at the moment between Earth and the spacecraft is 18.5 minutes. So each step means that you've got to wait for 37 minutes while you take the step and then wait to see what's happened in the consequences. It's going to be very, very painful. I think, Andrew, this is probably happening as we speak because it's scheduled for the 27th of October US time.
Okay.
We are the following day, so I think it's happening now. So by the time this podcast goes to air, the outcome might be known already. Oh, drat, we've lost it all. No, I'm sure it won't be that.
Oh, I hope not. But it's in terms of glitches when it comes to space missions, this is not the worst thing that's ever happened on a visit to another world or another object. But, there's been the famous cases of lens caps getting stuck on by heat and all sorts of weird and wonderful things. But it sounds like they've got a solution. And whenever you watch documentaries or movies about problems in space, it's always about working the problem. And they obviously have got an idea on how to deal with this. They're just going to have to be very careful with the execution.
That's correct, exactly, which is why they're doing it one step at a time.
Right. Well, we might have a follow-up to that yet again next week, so we'll keep a close eye on the OSIRIS-REx mission, which I think will only be the second time that a probe has brought back matter from an asteroid. I think the Japanese have done it once before.
Well, they've done it once already, and there's one other Japanese one on the way back, which will come down here in Australia, in fact, in December, I think. So,
right. Yeah. So this will be the third time in that case. Very good. Well, the more we get, the more we learn. That's what it's all about.
Free gifts.
This is... Sorry, go on.
No, any samples like this that we can get back, absolutely invaluable scientifically.
Indeed. Totally agree. This is the Space Nuts Podcast, episode 226 with Andrew Dunkley and Professor Fred Watson. Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
Space Nuts.
A big shout out to our patrons. No matter how you support us, we appreciate it. The patreon.com/spacenuts page is an option where you can choose as little or as much as you wish to contribute once a month, totally voluntarily. If you'd like to become a patron, Space Nuts is on patreon.com/spacenuts. There's also the option to go through Supercast, and there's all sorts of packages available through Supercast. Again, not expensive, but you can choose whichever. But it also gives you access to multiple podcasts, so you can buy a package if you want to do it that way, or you can just make a straight donation. I think PayPal is now an option if you want to do it that way. And as I say all the time, this is not a requirement. It's not something we want you to absolutely do as a must. It's totally voluntary, and we would not force you to do that. We'll never ever switch it to a pay-only service. So we just appreciate those people who have come to us and said, we want to give you something for the work you do. That's how you do it. All the details are on our website, spacenutspodcast.com. Now, Fred, let's tackle a couple of questions. This one I know you particularly loved. This comes from Ed Manson in Sydney. I've always been intrigued as to why the longest day of the year doesn't have the latest sunset time of the year. In Sydney, the longest day is the 21st of December, but the sunset time continues to get later in the evening each day for some time after this. I haven't ever really been able to conceptualize why this is so. Perhaps Fred could help edify me such that I can demonstrate my superior knowledge to my old man who has always asked this question, who's also asked this question before. Thanks. Now, I do recall we have talked about this, I think, on the radio years and years ago. It is a strange thing because after the longest day, the summer solstice in the Southern Hemisphere, it would be natural to assume that the days start to get shorter after that, and they do, but the sunset continues to happen later, and that's where he's confused.
Yeah, it is a great question, and it's you're quite right. It's one of those that I've always relished since I first answered it, actually, for a newsletter when I worked for Her Majesty's Nautical Almanac Office at the Royal Greenwich Observatory back in the 1970s, early 1970s. So and I might actually just do a plug because I cover this question in my book, Why is Uranus Upside Down? and other questions about the universe, which was published actually quite some time ago, back in 2007. But it's 150 questions that people asked us on the radio, and this is one of them. Why doesn't the longest day coincide with the earliest sunrise and the latest sunset? It actually, in the book's couched the other way. It's about the shortest day because the same thing happens. So let me give you the figures. Okay, for the summer solstice, exactly as Ed mentions, only I'm doing this I'm reading it from the book, so it's for 2007. So the dates are just very slightly different, but basically amounts to the same thing. In summer, the earliest sunrise is on the 6th of December, and this is in Sydney again. 6th of December is the earliest sunrise. So after that, the sunrises start getting later. And, you would think, oh, well, the days are getting shorter, but they're not. They're getting longer. And they're getting longer until the solstice, which is on the 22nd of December, and then start getting shorter, as you said. But the latest sunset is actually not until the 7th of January, the following year. So there's this skewing. The earliest sunrise is 6th of December. The longest day is the 22nd of December, and the latest sunset isn't until the 7th of January. And you'd expect intuitively all those things to be on the same date. You'd expect them all to be on the 22nd of December, but they're not. And it's actually a slightly complex reason, but it is all about the fact that the sun as a timekeeper is not very good. And we know that because if you have a sundial, the time that you record with the sundial is not the same as your clock time. And it varies throughout the year. It averages out to be the same over a year, but there are times in the year when the clock is running ahead of the sundial, times of the year when the clock is running behind the sundial. And the difference between them is something that for centuries has been called the equation of time. And you can plot a graph of the equation of time. In fact, anybody who's listening to this, if anybody ever does, if you check out on the web and you'll be able to see, just Google the equation of time, you'll be able to see the way it varies throughout the year. That equation of time is the difference between clock time and sundial time. And it comes about because the Earth's orbit, first of all, is not circular. The Earth's orbit's elliptical. We are closest to the sun on the 3rd of January and furthest away on about the 3rd of July. So it's an elliptical orbit. That means that the Earth's progression around its orbit is not at a constant speed. And that, combined with the fact that the Earth's axis is tilted with respect to the perpendicular to the Earth's orbit, that is what produces the equation of time. It's what gives you this funny little graph that shows the difference between clock time and sundial time. Now, okay, how does that relate to the solstice? Probably the easiest way for me to deal with this is to read it out of the book, since I wrote the book myself.
You wrote it, Fred, so they're your words.
Yeah. So if you can think about actually, I might just, let me just read what I've said. So it says, why doesn't this bewildering set of dates coincide? That's what the ones we've just given. The reason has to do with the sun's bizarre behavior in running fast and slow, as described earlier in the book. You'll have to read that. It's the good old equation of time again. At certain times of the year, the interval between noons on successive days is slightly greater than 24 hours of clock time. And at other times of the year, they are slightly less. The differences cancelling one another out over the whole year. Near the southern summer solstice, the time between successive noons is 30 seconds less than 24 hours. So that's the crucial part of this.
It's a big chunk of time.
It's a lot of time, yeah. So it's when the equation of time is at its extreme. And that difference, and so here's the crucial point, that difference of 30 seconds per day is greater than the difference between the sunrise and sunset times on successive days. And so the equation of time becomes the dominant effect, the fact that that's changing more rapidly than your sunrise and sunset times are. And the result of that is to stagger the dates of the earliest or latest sunrise and sunset times and the solstices. It works at both solstices. It's actually more pronounced in December than in June because of the larger discrepancy between the solar day and 24 hours of clock time. And here's another thing. It's less pronounced at higher latitudes. So it was something I never noticed when I lived in the UK at latitude 55 or so, whereas down here in Australia at latitude 33 or 34 in Sydney, you're at about 31 and you're about 32, I think, in Dubbo. That you get this greater daily change in the sunrise and sunset times, and this is the bottom line. If you were to plot tables of sunrise and sunset times based on sundial time rather than clock time, the effect would disappear altogether. So it's all about the fact that the sun, as it apparently moves around our skies, as you know, as seen with a sundial, is not a good timekeeper.
So if we never invented the clock, we wouldn't have noticed.
Yes, that's right. If we'd always relied on sundials, we wouldn't have noticed. But sundials are not good timekeepers. So it was really with the mechanical clock, the invention of the mechanical clock, that the idea of the equation of time emerged. That's a complicated thing, isn't it? It's not easy.
Oh yeah, my brain hurts.
Sorry, go ahead.
Yeah. No, my brain hurts just trying to.
Yeah, that's right.
I was listening as carefully as possible to try and get my head around it. But if you asked me to explain it right now, I'd collapse. And Ed, good luck explaining it to your dad.
Well, the best thing that Ed can do is give him a copy of Why is Uranus Upside Down for Christmas, because it's still in press.
Boom, tish. There's the sales pitch.
There you go.
It's a great question. I always, as you spoke and explained all that, my thought was, well, wouldn't a sundial always be 7 minutes behind, or 8 minutes because of the travelling time of light? But I don't know.
Well, yeah, sundials don't take that into account at all. People didn't know when they first invented sundials; they had no idea that the sunlight takes 8 minutes to get here.
Yeah, it's all sorts of things to consider. But thanks for the question, Ed. It's an absolute ripper and a much more complex answer than I think you might have been anticipating. Now, let's move on to our next question, and it comes from Brock Pedersen. Brock dropped an audio question down, but we haven't been able to collect those. So he very, very thoughtfully sent it to us in text just in case. And he said, on a recent episode of Cosmos with Neil deGrasse Tyson, he says that we could set up a telescope in space that uses the space curvature of the sun as a lens to view distant, far-off locations with extreme magnification. He points to the question why we haven't done this yet, as we have the technology. Do you know why we aren't doing this? And do you know why? What kind of resolving power we would get? Could we look at planets orbiting stars in the Andromeda galaxy, for example? Great podcast, you two, and I hope it goes forever. P.S. Fred, are you ever going to be able to guest on Stargazing Live again? Loved seeing you on it last time. Brock Pedersen. I think I saw you on it last time too, Fred.
Yeah. Well, hopefully, when Stargazing Live returns, as I hope it will do eventually, we'll see what happens. The last time Stargazing Live was on, I couldn't be there because I was actually leading an eclipse tour in South America. That was last year, so that's why I couldn't make it. I couldn't tell the eclipse to wait because I wanted to be on Stargazing Live. It just didn't work that way.
Refer to previous answer to previous question in regard to wait.
Exactly. Okay, so this is it's interesting, and it's certainly an idea that has been discussed before. Why hasn't this been done yet? Well, because it doesn't work. Not as neatly and tidily as that suggestion from Neil deGrasse Tyson comes about. I haven't actually seen the episode of Cosmos. The problem is, okay, you have a gravitating body like the sun, and first of all, it will be a lot easier to do this with the Earth than the sun, because the sun is a luminous object. And so if you're trying to, if you're trying to use its space curvature to bend the light from distant objects, you first of all have to get rid of the light of the sun. One way to do that is by means of an eclipse, and that's actually how relativity was first confirmed in 1919 by a total eclipse of the sun on, I think, the 24th of May, if I remember rightly. And so that was, in a sense, doing what this question is talking about. They looked at the way the images of stars were moved away from the disk of the sun by the gravitational curvature of the space around the sun. But the problem with that, so let's get rid of the sun, because that's a terrible idea. The sun's too luminous. But you might think about doing it with the Earth. Or even the moon, actually. The moon would distort space to some level that would let you actually form an image a long, long way from the moon, along the axis between the moon and the object that you're looking at, trying to study. But the difficulty is that it's not a lens as we think of it. It's actually, if you think of a lens in a telescope, it's a bit like a spectacle lens. It's usually convex in the middle. Thicker in the middle than at the edge to make it convex. That's the basic form of a telescope lens. A lens that would mimic the gravitational distortion of the sun is a different shape. And in fact, it's more or less the shape of the bottom of a wine glass. Somewhere I've got a broken off bottom of the wine glass, which actually simulates very well what the imaging properties of an object in space is. And it doesn't form an image of the kind that you can examine microscopically to look at details like planets orbiting stars in the Andromeda galaxy. What you get is what is called, what is it called? I've forgotten the name. That's ridiculous. It'll come to me in a minute. A piece of optical terminology, where you've basically the light forms a cusp. Gosh, I can't remember the name. It's on the tip of my tongue. Never mind. It doesn't matter.
Happens to me all the time, Fred.
Sorry, say again, Andrew.
Happens to me all the time.
Yeah. Okay, I've got it now. It forms a caustic. The technical name is a caustic curve image. And that is not the kind of image that you can magnify with, the kind of equipment you need to look at planets around other stars. There might be ways that you could modify that, correcting lenses, but it actually becomes an engineering challenge, which is kind of, on a hiding to nothing, because the more engineering you do to try and give yourself a proper image from the caustic image that you get, that you would get, is actually quite serious stuff. And in the end, it's a lot better to use a conventional telescope, like the extremely large telescopes that are on the horizon at the moment, where you can control the imaging properties at first hand. I'll come back to that in a second, because I want to point out one of the other issues with trying to use a natural object as a telescope, and that is that you've got to get your spacecraft to detect the image in the same direction or opposite the Earth, or whatever you're using as your gravitational lens, as the target that you're looking at. So you've got all the orbital dynamics of that to cope with as well. And it just basically amounts to being a non-starter. Neil deGrasse Tyson positing the question why we haven't done it yet has a lot of very sensible answers. And if you want, send him to me. I'll tell him why we haven't done it yet, because we don't have the technology. Absolutely not.
Bottom line.
And just one other aside on this is that, yes, we do use this phenomenon for, the magnification of very distant galaxies. We use it all the time. You and I have spoken about it, where you've got a cluster of galaxies and its gravitational distortion lets you see all these strangely curved images, which are caustics, exactly as I've described, of much more distant galaxies. And you can actually, at some level, reconstruct those images to give you some sort of idea of what's going on. We actually had I think we talked about this with a ring of light, an Einstein ring that was reconstructed into an image of its proper galaxy. We've done that already. But this is in situations which are very different from using the sun or a planet as a telescope that you can point around the sky. They're just taking advantage of a natural alignment. The technology does exist to reconstruct the images, but it's at very poor resolution because the difficulties are quite high. So going back to what I was just saying, with the extremely large telescopes, and in particular the European one, the ELT, which will have a mirror 39 meters in diameter, that will have the resolving power to see the planets of stars in the Andromeda Galaxy. It's phenomenal, the level of resolution that you will get with that. Now, it's a very difficult problem to do that because you've got to blot out the light of the star before you can see a planet. But the extreme resolutions that we will get with these ELTs, that will actually let us explore the stellar population of galaxies like Andromeda at close hand. At least it will if there's one in the Northern Hemisphere. The TMT, the 30-meter telescope, is the Northern Hemisphere equivalent of the European Southern Observatory's one down in Chile, the ELT. That's sadly held up at the moment because of issues with the location on the summit of Mauna Kea, which is all to do with the traditional owners. And it's a very, very difficult problem, much more difficult than imaging stars in different galaxies, planets in different galaxies. It's a problem that really has no easy answers. And it might result in that telescope being built elsewhere, perhaps on the island of La Palma in the Canary Islands, which is not quite as good a site as Mauna Kea, but still pretty good. I've got off the track there, but regular telescopes have got a lot to offer. The square kilometre array, likewise in the radio spectrum, will have very fine resolving power because its antennas are spread over a large area. So we don't need to worry too much about looking at gravitational lenses. They're a pain to deal with. And once in a while we get a fortunate juxtaposition that lets us see galaxies behind a cluster of galaxies and lets us get decent results from it. But it's not something I think you could use as a routine method of observing. There you go. That's a long answer to a short question.
No, but a good question and well worth asking. Brock, thank you so much. We appreciate it. And thank you to everyone who sends in questions. We're starting to pile them up again. But of course, as always, if you would like to send in a question, go to our website, spacenutspodcast.com. You can send it the traditional way through our contact portal, or you can click on the AMA tab and record your question. Just tell us who you are, where you're from, and ask your question. As long as you've got a microphone attached to your device that operates, we will receive it, and more than happy to go through them and pick and choose which ones get put on the air. We can't do them all these days, just too many. Although we had a little drought, but that's certainly not the case now. But keep them coming. That's what we like. Fred, that brings us to the end of what turned out to be a lengthy episode, but very, very good indeed. Thank you so much.
It's a great pleasure. It has actually turned out to be lengthy, hasn't it? That's good. Well, never mind. It's all good stuff. Thank you very much.
That's all right. It's
Andrew for.
It's because we're approaching the summer solstice, and not the length of our episodes is actually longer than they appear. That's what's happening.
We should be doing it by sundial and not by this little number.
Maybe. Yeah, that's how I tell the time on radio, by the way. Thank you, Fred. We'll catch you again next time.
Sounds great. See you soon. Take care, Andrew.
See you, Fred. Fred Watson, astronomer at large, here on the Space Nuts podcast. And from me, Andrew Dunkley, thanks again for listening. Tell your friends, say hi to your mum for me, and we'll catch you on the next episode.
Space Nuts.
You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.
Of all the gin joints in all the towns in all the world, she walks into mine.
Welcome to a new podcast for the movie lover in all of us.
Hi, Richard Kuipers here, host of the Classic Film Club. I'm a film critic for the international trade paper Variety, a documentary filmmaker, and I program the Freak Me Out sidebar at Sydney Film Festival. Apart from all that, I've been a film fanatic all my life. I'm especially interested in looking at old movie classics through modern eyes and shining a light on lesser-known treasures from the past 125 years of cinema.
The Classic Film Club, available via Apple Podcasts, Google Podcasts, Spotify, or wherever you get your podcasts from. For more details, join our Facebook group. Just search for the Classic Film Club podcast group or visit our website at theclassicfilmclub.com. The Classic Film Club, new from Bytes.com.